So without further ado, please help me in welcoming our speaker.
Okay, so let me share with you, and then we can figure out if I can make this in full screen without.
Perfect.
There we go. Thank you. Thank you for bearing with me. So I'm going to talk about the National Research Platform, and I wanted to start by giving you a very high-level overview of what this is all about. And so in my mind, NRP aims to address two challenges that have almost zero non-overlap. And the full disclosure, in the original proposal, we were barreling down the second one and had no idea that the first one was even possible and within scope and relevant and interesting. And so then as we started deploying this and talking to institutions, we ended up realizing that the much bigger value add of NRP is actually in the first. And so that's why I'm going to start with the first, despite that for this audience, maybe the second is as important as the first. In fact, maybe even more important. So I've written these slides a little bit with an eye towards major facilities, or I will at least talk to that, but I will give you a description of what we do, strongly focused around what currently is the biggest focus, which is providing an AI education research infrastructure to all of academia that academia can actually afford. And so let me start by that, education infrastructure for all. And let me go there by playing with some numbers, just to get you oriented. In the United States today, there are 20 million students that attend college. And out of those, if you then ask yourself, so how many of those is likely to want AI education one way or the other? San Diego State University did a formal survey with 8,000 student responses. And in that formal survey, among lots of other questions, they were asked, would you want some sort of formal training in AI? Or actually, the exact question was, would you want to have more formal training in AI? And 50% of the students said yes, in one way or the other. And so the other number that you can take is UC San Diego undergrads have enjoyed a platform, essentially, that's a carbon copy of NRP, and that UCSD runs for only its education program. We've been running this since 2017, well before AI was, well before ChatGPT. And at this point in time, in AY24, 22% of all UCSD undergrads have used data compute in at least one course where they were required to use the infrastructure I'm talking about as part of their classroom education. So if you then multiply these numbers, you get to somewhere between 4 and 10 million college students in the US need data and compute resources for their classroom education. That's a pretty solid number. And it is a number that is big enough to justify attention from a supercomputer center, because we are all about scalability. And so developing means to scale out to large numbers or large performance or large something or the other is sort of in our DNA. And so that's why this is an interesting thing for us to get involved. Now, what are the options? Well, cloud is too expensive for academia unless the NSF pays the bill. We're the proud host of NSF Cloud Bank program. So I'm all for cloud and somebody else other than my institution or me pays the bill for the cloud bill. So if the NSF wants to spend money on this, more power to them. However, if I have to spend money on this, I'd rather not. And the argument is simple. It's when I look at the latest NVIDIA HEX platform, and renting that one system of that type, you spend in 100 days about as much as buying it. On the other hand, when we operate it on-prem, we typically run for 6 years. If you divide 6 years by 100 days, you get about a factor 21 or so. And so there is roughly a factor 20 out of the gate in cost savings. And then you chip away on this. You need somebody to operate it. It costs power, da 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 da. And so, in addition to the pure cost argument, for a lot of the colleges we deal with, there's another argument, and I want to describe this in analogy. When you rent and run out of money, you become homeless. When you own and run out of money, you still have a roof over your head. In other words, you can do deferred maintenance, deferred replacement, and stretch out if you're out of money in order to actually get value out of something that you own. Whereas you cannot get value out of something that you rent when you're out of money. You're done. And that has lots of ramifications which make the cloud unattractive. Now, so operations is expensive unless it is amortized across large scales. Basically, there is a lesson to be learned from the cloud providers themselves in that if you very superficially, high level, buying twice as much hardware costs twice as much money. Operating twice as much hardware costs about log 2 as much money. In other words, there is sort of the growth in operations funding, operations labor is very much below linear as you accumulate more and more and more hardware under management. So what that means is that given that at the very beginning, these 20 million students are currently going to college in 3,800 institutions in the United States of America. If you divide the numbers, you get to, on average, institutions that are way too small to actually operate hardware, but they're perfectly capable of buying hardware. And so what we've realized is that fundamentally means that if you could aggregate the system administration, cybersecurity, and the user support across all colleges, and I'm a physicist, I like to pick numbers with 1 in front and then zeros. So 1,000 colleges, then you could actually amortize the operations cost to something that is basically free per amount of hardware that you're managing. And so what we've created is we've created a system, a set of processes and technologies where we can run hardware from remote and can do so and achieve the kind of aggregation that is required in order to make owning of hardware affordable for every single college in the country. And I'll tell you in this talk how this works a little bit. I'll tell you where we're at. And while I came towards this realization via the argument of AI education, the very same thing applies to research, and applies to research even more so, because if you think about this from a business perspective, colleges can have one product. That product is degrees. They can make degrees more expensive and therefore build owning hardware into the cost. However, research, by its very nature, is always done out of the margins. In fact, the only price that any of the faculty that I've ever talked to understand and appreciate is free. Anything that costs more than free is basically, I get shown the door to first order, at least in my university. And it's very hard to get faculty to actually understand that they have to actually pay for resources and pay for infrastructure. That's just not something people are willing to do. And so my pitch at a very high level is, let's create an open infrastructure that is horizontally open to all of academia and vertically open to build upon. And that can include all of open compute, open storage, open content delivery networks, open devices, instruments, IoT. And with open, I mean anything that doesn't have a lawyer involved. Because the moment they get the lawyer involved, there's so much crap that you have to deal with that it doesn't make sense anymore to operate as a distributed infrastructure. In other words, if your data is regulated, then this is not a viable option. And the costs of doing science with regulated data skyrocket instantaneously. And so I'm not even trying. And so what do we have right now? NFP offers the community to run your hardware from IPMA Hub. What this means is that we work closely with the research and education networks. And because we require two things from the institution before we can operate their hardware. One is that we do not want to deal with accounts, because management and maintenance of accounts is costly. And given that we want to have absolute bare bones cost structures, we delegate, federate account management with the institutions. If you have EduRoam, then you have federated account management, and we can work with you. Basically, anything in common CI logon is a requirement for us to be working with institution. Because in all of our services, people log into with their institutional credential rather than with a credential that we give them. And the second requirement, and why we work with the networking providers, we require Science DMZ in order to make the global Kubernetes cluster work, because that's just technical. And so then what we give back is researchers, educators, and students see a global scale Kubernetes cluster. There's lots of software to reuse in form of either Helm charts, containers, GitHub, we maintain lots of topical chats. We run our own quote unquote Slack. There is an open source version of Slack, which is called Matrix. So we run Matrix for the community, and then we give the way that we enable people to have classroom education on the infrastructure is every classroom gets a chat room, and the chat room is managed by the instructor, and that's how the instructor deals with the students. And that's how we deal with the fundamental scalability issue of having a classroom of 1,000 students and having 1,000 classrooms. We can't have a team that does that, but we can have a team that actually can deal with instructors. And so each instructor has a chat room for their class that they manage, and then we have chat rooms for the instructors to talk to each other. We therefore have effectively I like to think of it as a digital water cooler around which people can meet, exchange best practices, chat, and help each other. And we guide those. Whenever disinformation starts happening, we get involved, but fundamentally, we aspire that the user community talks to each other and the community supports the community such that it brings down the price of the total infrastructure. And then finally, we do LLM as a service, and I have some more on this. At this point in time, we find that there's an awful lot of education that already uses LLMs in the classroom in very creative ways, and I'll give you an example later. But let me first give you one slide of more technical information, and that is our software stack. And if you look at the software stack, in 20 years or 20 some years, as I've forgotten, no, actually 20 years pretty much exactly of OSG, the one thing that I've learned is that OSG struggles in engaging with institutions because not every institution can provide and manage batch and storage clusters and administrate this because they don't have the effort. And NRP does exactly the opposite. It starts with managing the hardware from the bottom up. But given that not every institution has a cybersecurity stance where they would allow you to do that, we have conceived of a software stack that has OSG at the top and NRP at the bottom, and allows people to pick where they want to integrate. And then they can benefit from the overall national scale infrastructure in different ways, depending on where they fit in. And my experience is that the rich folks tend to have heavy-handed cybersecurity requirements, whereas the less rich folks are very happy to let us run their clusters all the way from IPMI up, because that's the only way that they can have clusters, because they don't have the means to actually operate that themselves. And so then let me talk a little bit more about AI. This day and age, everybody has to talk about AI all the time. And so here's the AI services as I conceive of them. Meaning in my head, there's 3 buckets of AI services. There's all the stuff that we've always done with HPC and high throughput computing, whatever, compute storage, Jupyter, Matrix, all the stuff that we do irrespective of AI ever being talked about. That's the initial set of services we started with NRP. Then as you dive into AI, it doesn't make sense that everybody and their brother and sister runs their own LLM, downloaded from Hugging Face, instantiates it on the hardware, and it's a waste of hardware, basically. So what we've gone to is we run LLM as a service for the community. In fact, we run about 10 of them, 10 different ones, all of them open weight. And we're happy to run a new one if you need it for something. And we'd use some of the hardware that we own ourselves in order to run this, back it up. In fact, the one piece of infrastructure that we pay for is Light LLM. We have an enterprise Light LLM license in order to integrate with commercial services like ChatGPT. So if you happen to have a commercial license for ChatGPT, you can use our infrastructure, use our LLM and our Light LLM license, and attach to your ChatGPT license in parallel to seeing, say, DeepSeek, and play around with both. And finally, I have this notion, or we have this notion as AI workflow as a service. As you move beyond LLMs, almost everything that you can do with AI is in one way or the other a workflow. And so given that we are trying to cater, at least in part, to an academic educational environment, or customers, we want to make AI workflows as simple as possible. And we're leveraging something called the National Data Platform. And I'll show you some things about this. I think I may have some slides. No, actually, I took those out. The NDP is basically offering curated data models and a UI that allows you to run workflows anywhere from your laptop to the supercomputer. And the default is NRP, where they run workflows on. And so the aspiration of NDP is to basically adapt and adopt anything and everything that comes out of the AI open source ecosystem in terms of workflows, and make them such that they're button clicks in order to incorporate into coursework and research. So this is what this looks like on NRP. In fact, if you want to try it out, I left at the very top the URL. If you go to this URL, you will be most likely asked for your in-common authentication. In other words, you authenticate with your institution. At least that's what happened when I did it the other day. Then basically, it requires you to authenticate when you click on the button, visit the LibreChat interface. The next thing that you'll see is something like this. Once you've authenticated, etc., and that then allows you to choose a model. And my favorite thing to tell people to do is try out DeepSeek and ask it about Tiananmen Square. It's very amusing what the Chinese government allows DeepSeek to talk about. And I've tried to get around it. I haven't found a way. You always get the same PR bullshit from the Chinese government when asking anything to do with Tiananmen Square. Now, a real use, an example complex classroom use, Carl Böttiger from the University of California, Berkeley, teaches a course with 122 students. It's an active learning classroom. In other words, it's, as you can see in this picture, Carl runs around in the classroom and helps people do exercises. And one of the exercises is he wanted students to learn how to visualize a 3D map of buildings in New York City, Manhattan. And they start with a vanilla LLM that has no clue how to do this. Then they teach the LLM how to do this by providing a context via some useful software packages. And then you get to see this sort of in your Jupyter Hub, in your Jupyter Notebook, basically. And voila, the LLM gives you back code that you can then execute in order to get this visualization. And voila, the LLM has learned how to provide working code for Jupyter, combining multiple packages and doing something that's highly non-trivial that I would claim that no student in this class could do by themselves without the LLM, because it's just too complex. And what this means is you can bring to the classroom things that you never dreamed of covering, because you have computing and data and software writing at your fingertips in ways that we've never had. And so what does it look like? This is NRP as of yesterday. It has a global geographic distribution of 84 geographic locations, 439 nodes, basically 1,500 GPU, 29,000 cores, and there's 22 petabyte of disk space in the system. And if you want to look at this yourself, you can follow the link. This link here will get you to a website that has this map attached, and the map is interactive. So if you zoom out, then you get a map like this here, and you see Hawaii, Guam, you see Korea, you see Singapore. And the reason why that may be relevant to some of you is some of the scale out of this infrastructure was actually driven by MREFCs, in particularly LIGO and Dune, in that they wanted to use OSDF, the Open Science Data Federation, on top of NRP in order to have global workflows that have automatic attachment to data via the features of the Open Science Data Federation. So they used essentially Open Science Data Federation as a content delivery network on hardware that is managed by NRP and donated by collaborators. And so if you look at some of these, places, if I move this away, the two caches are OSDF. There are nodes in NRP, OSDF on top, showing horizontal openness of the NRP, and then part of with all of these other caches that you have everywhere here, and the caches in Singapore and Korea provides LIGO with a global infrastructure where where data movement is automatic. And now let me go to an example how a smaller institution uses this. CSU San Bernardino is a non-R1 institution, like an hour and a half drive from San Diego, and it's a 57% Pell Grant recipients institution. And they've built into this with a vengeance, and have at this point, they have a generic Jupyter Hub branded for CSU San Bernardino as the entry point for the entire campus. And then they have a bunch of different dedicated hubs for different labs. In other words, they have one for all, and then they instantiate as needed things for different research activities on campus, and have built the entire research infrastructure into NRP and on top of NRP using Jupyter. And where does this get you? This here is a plot of, it's a log plot. On the y-axis is the number of GPU hours consumed. On the x-axis, the number of CPU cores consumed. And here's your CSU San Bernardino as an institution. San Bernardino as an institution, and non-R1 has consumed about 100,000 GPU hours in 2024. And if you look around in the neighborhood, there's San Diego State University, which is a small R1, and they became R1 for the first time a couple of years ago. There is CSU North, which is not an R1, and here's sort of California. We have a large contingent in California simply because of history. It was adopted first in the Great Plains and in California. And so predominantly, we tend to have institutions from the Great Plains and California. Say, for example, the University of Missouri and so forth. Now, you can orthogonalize this differently, but before I get there, there's one feature that is interesting because coursework activity tends to follow a pattern across the quarter. At the beginning of the quarter, when everybody is just getting accustomed to this new course, nobody uses the infrastructure. And then you have sort of peaks around midterms and then finals, and it's sort of towards the end of the quarter, things get pretty heavily used. But by and large, there's a lot of leftovers, and there will always be a lot of leftover capacity for research. So by building an AI education infrastructure for all colleges that is affordable, at the same time, we've built an AI research infrastructure for all colleges that is affordable, and that is basically has free capacity whenever the teaching is not in session. And so we're bringing in research in the back door and giving these colleges capabilities that they've never had. And so you can turn this around and then ask in terms of each and every one of these, now the same log plot, but each and every one of these dots is a namespace. Basically almost all research namespaces. So when I talk about NRP these days, I talk mostly about education. The dominant use is actually research still by a huge margin. And you can sort of see some of these are your colleagues, so to speak. There is a bunch of observatories. I think if I remember correctly, we're talking about LIGO, IceCube, and NRAO as the dominant and users of these three stars. There's also USRA, which is actually a very large user, and maybe one of these stars is them. I'm not 100% sure. Then there's a bunch of community software packages where people who own those packages use those packages in order to produce data that is then shared with the community. That's sort of the pattern. And there's a number of large ones that have significant use. The one that I remember is open source. What's it called? Open something field in life sciences. I can't recall it. Apologies. And I think that's this star here. And the message here is that each and every one of your projects could be an NRP users and simply consume the leftovers, OSG style. In fact, you can, as an OSG customer, if you happen to be a high throughput computing shop already, you can use OSG to consume the GPUs on NRP. And this goes back to, where was I? While I talked about this stack from the perspective of incorporating hardware, this also is a stack from the perspective of user communities. So your communities could enter either at the top here via OSG and Path, or at the Kubernetes layer via an NRP natively. NRP supports natively kubectl and Jupyter, and then a few more esoteric things like Coder, and we have some FPGAs where we support various types of different things. But the dominant use is kubectl or Jupyter in terms of, and then OSG. is the dominant consumption. If you look at these stars, some of them are use kubectl, and some of them come in via OSG. Now, where are we going with this? The way I look at it, it's a three-phase project of executing on a vision. We're in phase one, where we're establishing concept and scale out to about 100 colleges and 10,000 students per year. And of course, whatever amount of research we have leftovers. Today, we operate hardware at 53 colleges across 84 locations. The difference between 53 colleges and 84 locations is that we have hardware in point of presence from basically in the RENs. If the name REN doesn't mean anything, it's the Research and Education Networks. Things like Scenic, Great Plains Network, SOX, MCNC, those kinds of places, we have hardware in their networking point of presence, basically in their network backbone, that we control and operate via Kubernetes. And of course, we have a fair amount of hardware inside Internet 2 at, I want to say at least a dozen POPs of Internet 2, if not more. And then the phase two would be a scale out to 1,000 colleges and 1 million students per year. The notion here is, if I want to make this free, but don't want to depend on the federal government, and for those of you who have not lived under a rock, you will appreciate the notion that nobody wants to depend on the federal government long term if they can help it, because well, it might not be there tomorrow, or it might only show up at half the funding that you had last year. And so we envision creating a sustainable operations via nonprofit and membership fees. And when I ask myself, what is cost as low that it's free? A beer a year is free, because I don't know anybody who drinks beer and drinks less than a beer a year. And so if I'm talking about 1 million students per year, and I charge every student a beer a year, San Diego, $8, $9, $10, that's about a beer. And then I get enough membership fees income to actually sustain this as a 24/7 operated system in cybersecurity operations and a 9-to-5 user support and training operations forever. And the reason why this works is, again, the very simple realization that if operating hardware gets cheaper, the more hardware, operating hardware gets cheaper per amount of hardware, the more hardware you operate. And when you hit about 10,000 GPUs, the operations is actually dirt cheap per GPU hour. And that's the kind of thing. Whereas buying hardware is linear in the amount of hardware that you want to buy. Twice as much hardware costs twice as much. So the colleges should own their own hardware, because because you don't want to be in the business of depending on the federal government to pay for 10,000 GPUs. That doesn't make any sense. And at the same time, a centralized operations crew is basically free to the colleges when done right with a lot of automation using Kubernetes. That's basically what this boils down to. Now I switch topics and go to the technology background. This is how NRP originally was conceived of. There is no E in NRP, right? Because it's a national research platform. It wasn't built or invented as a national education platform. We just happen to do that now. And so this really was where we came from. And so the original idea was that NRP brings computer science R&D and domain R&D onto the same platform. And this was motivated by the realization that Moore's law is dead. And as Moore's law is dead, you have a proliferation of hardware architectures that no sane that a domain scientist wants to deal with, because there's too much change and churn in the totality of the technological landscape. And so we felt that let's build an infrastructure that is both testbed and production CI for the domain scientists and testbed for the computer scientists to play. And let me sort of back up a little bit of where my thinking comes from. Very, very, very superficially, I look at science and progress in science as being a product of algorithms times hardware. If you have exponential performance growth at the same cost in the hardware, then you don't need to improve your algorithms because you get your exponential from the hardware. This is what the life we lived for decades, because of Moore's law, first the combination of the NAS law and Moore's law, and then Moore's law only made hardware performance twice as good for the same amount of money 2 years later. That has stopped, and I'll show you some slides, on the next slide, some data on this. And the end of Moore's law threatens scientific progress because no more hardware progress. So now the name of the game is you have to make algorithmic progress, because hardware progress is dead unless you want to fundamentally change how you do things. And I'll talk about that in a second. So that's the algorithm exponential that you now need, because there is no hardware exponential, is AI. AI has the promise that it will be exponentially cheaper over time, or cheaper by factors of 1,000 at a time, because you get clever and you don't do in your reconstruction or whatever else you do the kind of heavy lifting that you do in the past. And so now a word about Moore's law. This is a plot that I stole from John Schaaf, which he presented at Supercomputing 23. And I like that plot because it makes it totally apparent what an enormous impact Moore's law has had. What this shows on the y-axis is the performance increase of the top HPC systems in the world in 11 years. Basically, what was the performance of the top, I forget whether it's top 100 or top 500. I don't know, does it say anywhere? No, it didn't put it down. Anyway, of HPC systems. And then what was the performance 11 years ago? What is it now? What's the ratio? And that used to be stably about a factor 1,000. So in 11 years, you got a 1,000 performance increase for free, basically, because the same amount of money was invested into the top HPC systems, roughly speaking. And then at some point in 2012, it decayed away. And the factor 1,000 turned into factor 10 or so over 11 years. That's what I mean by Moore's law has died. And if on the right side, there is another way of looking at this, which comes from Mark Papermaster, who's the CTO of AMD. He's basically in charge of all technical things in AMD. And he had this slide at a Dell event that I went to a few years ago, where he argued that once upon a time, you had general purpose CPUs. Then with the end of Moore's law, you had to use the silicon more restricted. That's where the GPUs came in. And GPUs fundamentally can't do everything, but they do what they do at a much higher performance. And he predicted a few years ago already that the future is in domain-specific architectures. And if you look carefully, we see this today in a number of different places. The obvious one is the iPhone. The iPhone has a number of different processors in there, all but one of which are not general purpose. They do very specific things. And another place where you can see this is when you look carefully from generation to generation in NVIDIA hardware, it actually gets worse if you need FP64. The performance per GPU hardware, if you go from the A100 to the H100 to the Blackwell, the performance in FP64 is not improving. It's getting worse because NVIDIA makes the conscious choice to put all of the oomph in the silicon into lower precision and floating points because they want to support maximum scale out of just one application, and that's AI. And so NVIDIA is basically building AI hardware today and no longer GPUs in some funny way. So now what else is happening? We conceive of NRP having something like an advanced technology laboratory where we acknowledge the fact not only do you have this here happening, but also as a result, every single peripheral device is becoming smart. And that has two reasons. Reason one is the peripheral makers, the companies that make your dumb devices, have seen that all of the margin, the profit margin, lies in computability. So they're creating things where they have larger profit margins. And two, because there is each and every one of these new type of programmable devices comes with a new programming paradigm that is being created in order to have specialized architectures to squeeze more out of the silicon that you have, because you're not getting twice as much silicon for free every 2 years. Every 2 years, that's gone. And so now, as a domain scientist, this gives the fear of God into me, because I don't want to have to deal with any of this shit, because I don't want to be in a position to adjust my domain science workflows to computational storage, to data flow programming, to programmable networks. There's an awful lot of technology here that I would now have to invest into significantly if you wanted to exploit and figure out how my domain science can actually make use of this in order to get the science done. Because Intel or whoever, NVIDIA, doesn't give me a factor 2 for free every 2 years anymore. And so that sort of was the motivation behind, part of the motivation behind NRP. The computer scientists love this stuff. Can we build an infrastructure where the computer scientists are as happy to use it as the domain scientists, and maybe we create social cohesion and therefore create pathways for adoptions that are less painful for the domain scientists and actually engage the computer scientists in a meaningful way. And I'm not sure that we've accomplished that, but this is an aspiration. And let me give you some examples. We actually, as part of NRP, we operate a 400 gig wide area network infrastructure, sort of as an aside. We own 400 gig capable nodes in Massachusetts, Geneva, Switzerland, and at SDSC. And we have partners who have 400 gig capable nodes elsewhere in the country or the world. And so we effectively have built a 400 gig testbed for experimentation that is directly linked in via Los Angeles. I own a 400 gig switch in Los Angeles where I peer at multiple 400 with the SNet Fabric, Internet 2, Pacific Wave, you name it, anybody who reaches Los Angeles. And therefore I can do things at 400 gig. And then I have a privately owned, basically privately separated 400 gig just for myself to Los Angeles. So I can do experimentation in 400 gig from SDSC to Geneva whenever I feel like it, because I have a standing 400 gig, so to speak, to my perusal. And I'm willing to share this with others who want to do experiments. And right now I'm sharing this out via Fabric in order to reach computation for Fabric experiments. Another example, we have FPGAs, as you saw here. We have 32 U55Cs and 24 Bitware 520 FPGA cards that have FPGAs on them. And we do, I'd call it applied computer science research with FPGAs on the infrastructure. And we support others to do the same. In this case, we have done a paper with programmable FPGA SmartNICs in order to do to show that P4 programming in SmartNICs can be used in order to do machine learning in the network backbone on the fly via infrastructure like this. In addition, we look at one of the big questions in my mind is, how do I bring the price down at the hardware level for inference? To me, the AI training train has already left the station. At any significant scale, nobody in academia does training anymore because, well, who has 10,000 GPUs at their perusal? And I can actually quantify. There's a plot that Ian Foster has shown at various conferences that the number of models at the leading scale that were produced in academia has gone to basically zero over the last 10 years. And so the name of the game in academia is now, how do I support scalable inference at a price that academia can afford? And so we're starting to explore inference hardware, because if you go back to Papermaster, inference, AI inference is the one application that I can think of in academia that is so ubiquitous that is actually worthwhile having dedicated hardware for. Most of what we do is very hard. There's very few examples of application that would justify the price of going to FPGAs or going to some esoteric hardware in order to do a domain-specific hardware implementation. You maybe get this for gene sequencing because there's enough gene sequencing in the world and a few instruments like that, and you get it for AI inference. So it behooves us to study and keep track of the inference marketplace, if you wish. And we buy hardware that fits into our price point, if you wish, and then explore how that compares in performance, power, and price. Because ultimately, I'm looking for something that I can build a inference service that can serve 1 million people, my million from earlier, 1 million students at an affordable price. We've played around with this Qualcomm Cloud AI 100 card. There's just now the follow-up card coming out. In fact, the NSF announced a Category 1 system, which is the follow-up at Stony Brook to the ARM system that they had as a Category 2. And that Category 1 system that was just announced literally days ago includes some of the AI 200 cards from Qualcomm, the next generation of these cards, in order to support inference in hardware in a platform that isn't NVIDIA or AMD. And summary and conclusions, what drives me in the education space is the realization that opportunity is a requirement for social mobility. At this point in time, I do not know anything that is comparable to education as an effective guarantor of social mobility. Nothing beats education if your goal is to create social mobility in the United States of America. Data and compute is increasingly required for education, and this was coming even prior to ChatGPT, and AI has just made this explode. It's like pouring gasoline onto the fire that already existed. I predict that education will change totally over the next 10 years, in that over vast swaths of all domains, you will not have classrooms without computing data anymore. And more, maybe 50% of our classrooms will actually involve data and compute 10 years from now. And any institution who can't offer this will basically die, because nobody wants to have a degree where you can't have that, because it's the norm. And so what we're doing right now is at the right time to scale out, because it's mandatory in order to maintain social mobility. It's mandatory in order to maintain education of 20 million students in the United States of America. And if we leave it to industry, nobody will be able to afford. And I've set the other things about algorithms and so forth. And thank you very much.
Wrap this up. Thank you so much, Frank, for your great presentation, and we'll see you all at the next one.
Thank you.
Thank you.
Thank you for
Bye,
having me.
everyone.
Bye.